Okay, so continuing on with our 11.1, we're going to talk about Emery trees. So an Emery tree is a type of tree that has a limit on the number of children vertices can have. So M would need to be some specified, sorry, there's a bit of fluff on there, some specified positive integer. And an Emery tree is one in which vertices have no more than M children. So we're going to look at an example of that where m equals 2, called a binary tree. Binary trees are especially important in computer science because we do a lot of, there's some data structures that are built around binary trees, which we'll get to shortly. So another definition here is an Emery tree in general is called full if internal vertices have exactly m children. So here are two examples of binary trees. You see in these graphs, our vertices have up to 2 children. They can have no children, like in the case of leaves, and some of them can have 1 child, like in the case of this vertex here that I'm pointing to, only 1 child. Also this vertex here, only 1 child. So since in the tree on the left, some of the vertices do have only 1 child, this is not full. But the tree on the right, you'll see I've taken the tree on the left and just added in a couple of extra vertices that weren't there before. Let me circle them there. So I've taken this tree and I've made it full by adding in those vertices that weren't there. There's some applications where you want to take a tree that isn't full and make it full by adding in some like blank or empty vertices. This is something you might do if you were like trying to store a tree structure in an array. You might have some entries in the array that are sort of dummy or blank entries. You might assign like them to null. And they're just placeholders so that you have the numbers all working out perfectly. So there's a binary trees not full and full. Now, I'm going to go through a few other definitions here. First of all, the level of a vertex is defined as the length of a path from the root. So for the root itself, the level of that vertex would be 0 because the path from the root to the root is length 0. So our root here at the top, that is level 0. Then these two vertices are level 1, and down here, these 3 vertices in the next generation down are level 2, and then our next generation, so to speak, is level 3. So I'm drawing the levels over here for this graph on the left, but you could do it the same for the graph on the right. And then, if you look at the maximum level obtained in that tree, so here it's 3, that is called the height of the tree. So this tree is height 3. Okay. So now, for trees, for Emery trees like this, and for binary trees in particular, we sometimes care about whether the tree is balanced or not. And balanced means that all of the leaves in the tree are at level equal to the height or height minus 1. So in my definition here, I say level h or h minus 1, where h is height. So looking at our leaves, let's take our examples here, and I'm going to circle the leaves in red. Our leaves are all at height at level 2 or level 3. Height is 3, so this is balanced. If I look at the graph on the right and circle its leaves, it has more of them, but they're still at level 2 or level 3, so that one is also balanced. In order to have this property, there needs to be, you can't have a lopsided tree where starting from the root, you have a bunch of vertices on the right-hand side and not as many vertices on the left-hand side. If you count the number of vertices on each side, it should be close. It's maybe not exact, but it should be within, I think, 1 or 2 vertices. So like for this tree, count the vertices on the left-hand subtree. So starting from the root, look to the left child here and look at that. how many we have there, 1, 2, 3, 4. And in fact, on the right subtree, we have 1, 2, 3, 4. So that's why it's called balanced. We could have had like 4 and 5 by placing another vertex here. Let me put that in purple. If we have another vertex like that, that would still be a balanced tree, but it's within plus or minus 1. So that's why they're called balanced. Let's just do a quick example of an unbalanced tree. So here, I'm going to, I've so far got, level 1, level 0, and level 1. But now I'm going to take one of the sides, one of these children, and put a bunch more vertices beneath it. So there's a couple of vertices beneath that one. So far, that's still balanced because now we have leaves on level 1 and 2. But if I put further vertices beneath this, now that is unbalanced because I have leaves on 3 different levels. Level 1, level 2 here, and these 2 down here are on level 3. So unbalanced tree. And if you check the left subtree and the right subtree, I have 1 vertex versus 5 vertices. So again, that's why it's unbalanced. We'll get back to why balanced trees are important when we talk about binary search trees in the next section. So one more definition here for this video, and that is ordered rooted trees. So far, our mathematical definition of trees are unordered. So you could take the tree and take any subtree and you could sort of reflect it around, like take these and just reflect this whole thing, mirror reflection over the root. Or you could take any other vertex and consider the subtree at that vertex and reflect that. And that would still be technically the same tree. But if you want to have an ordered rooted tree, then the children of every vertex are ordered, and then doing a reflection like that would change the tree. When you are actually using a tree to store data in a computer, it's ordered by nature, because in a computer, I mean, when you are storing an array or something, you can't have an unordered list. Like that just is sort of impossible in the case of a computer, right? The computer puts an order on it because you need to have an index which tells you where things are in the list, and you use that index to refer to things in the list. So everything is really ordered by nature in a computer, so we use ordered rooted trees for data structures. And for binary tree in particular, the vocabulary is left child, right child. So that's it. See you in the next one.